All right, so we're recording now. Okay, so we're going to start the class. Let me go ahead and share the screen here. Right. All right, so last week we started the second third of the class, right? The sequence of neural networks. And basically, so you can check out that video if you missed it, but basically the idea there was to motivate how we can take any model, just a machine learning model built in TensorFlow, and deploy it to the web. So you had a homework assignment, which is basically to, just replicate what I did. So hopefully you guys were able to do that. Make sure you complete that. All right, and then as we go through the semester, you should be deploying all your models whenever you can, and we're just going to start looking at, if we do images, for instance, we're going to need to know how to load an image, things like that. But otherwise, you got the basic pipeline of how it works. So what I'm going to do today, though, is I'm going to start with, since we're in this second third, we're just focusing on neural networks, right? I'm going to start with a little bit of the theory of neural networks, and we're going to start building our models. Okay, so last week on Thursday, we did the classifier for numbers, right? So we wanted to see if it was even or odd. Just very simple. But now we're going to start building neural networks, right? So today, so obviously today and Thursday, right? So we're starting our sequence of neural networks. Okay, so we're going to learn what a neural network is in definition, and we're going to do, to kind of motivate that, we're going to do the classic example of the XOR algorithm. So you all know what XOR is, right? The XOR operation. So we're going to build a machine learning algorithm that can, basically tell you something about XOR, right? So we're going to think about that, a classification problem, okay? So that's basically the idea, and that will motivate. So basically, how do we build a classifier for that? Actually, it's a classic example because, as it turns out, we cannot solve XOR unless you use neural networks. That's basically the intuition, right? That only neural networks are capable of solving that problem. Okay. So we're going to get started. What a neural network is, right? So I'll give you a little bit of theory. We're going to do some examples. Just you should know what a neural network is beyond just, you see the fancy pictures of a whole bunch of neurons, right? That look like the brain and all these connections, and it just seems like, what is that, right? Well, there's also a formal formulation of a neural network, and that's really what we want to understand, because everything that we do with TensorFlow and our code that we're going to be writing is basically going to revolve around this very simple idea that you already know, right? So you guys already know this, and you just didn't know that was a neural network. That's kind of how it turns out, okay? And we want to understand really what it is that actually makes it a neural network, okay? So anyway, so the code for this week will be this. Right, we're going to start here, and then from here we're going to build up. This is just a motivation. From here we're going to start with the perceptron, linear regression, logistic regression, and multi-layer perceptron, deep learning, right? But all of it implemented in TensorFlow. All right, and as I go through it, we're going to do some types of different problems. Today I'm not going to read any data in. Instead, we're just going to generate the data automatically. This is going to be that XOR data. Okay. All right. So we're recording and everything. And okay. So the neural network, right? You guys have heard, a lot of things about neural networks, right? And basically, they're an idea started around the 50s. I'll go over. I have a thing about the history. I'm just not going to do that today. I'll probably do it on Thursday. A little bit of the history is really nice. This should be a Netflix series at some point. It's gotta be. It's actually very nice, right? It's very interesting. There's stuff going on. Starts at Bell Labs, and and there's a whole bunch of different things. So I'll talk about that, but not today. All right. So anyway, so the neural network, we always have this notion that it's, some kind of a cell with connections, right? And this is happening in the brain somehow. And this is kind of what you always see in books and things like that. But really, as it turns out, the neural network is just, a function, right? It's a function that you have inputs and then you have an output, right? That's a neural network. Well, that's actually just a sum of variables, but then there's a couple of very simple things that you do to that function that make it into a neural network, all right? It has the ability to learn things. So we're going to motivate this by the same problem we've been looking at for a while, right? So you guys intuitively already know you have some data like this, right? And then you know how to model linear regression, right? You put a straight line, you basically do this, right? You put a function that goes through the data, and that's a linear regression. Usually you also know that there's an equation for the line, right? Do you see that? Well, then now we're basically doing something very similar, but with the difference that now we have in the classification problem, we have data like this because it's a classification problem. You see? And then the goal is, whereas with linear regression, we would still build a line, right, that goes through it, right? And this would be y equal mx plus b, and we would find that for that objective. For what we're trying to do now, which is classification, that is to separate x's from zeros, we do something different, right? Instead of a line like that, we want a line like that. Do you see that? So it's so you can think of as using the exact same function, but just turning it in such a way that now it allows you to separate things. Do you see that? Now you can create as many lines as you want. You can create this line, that line, that line. They all pretty much work, right? And so you have an infinite number of lines that you can figure out. How do you figure that out, the line? By calculating these parameters, right? And also remember that because we are dealing with multiple inputs, features, it actually becomes, oops, W2, X2, dot, 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 WN, oops, run out of space. Wait, hold on, I ran. Doesn't let me write so far. Well, I'll write it down here. It's not letting me. XN, right? So that's that last part. Do you see that? So we have this equation basically, right? That's the same. That's an extension of the line equation, right? Because we have with this implies that the vector space, this is R2, and this implies this is Rn, right? So it's an extension of the vector space. But what I want to stress is that in a simple example with linear regression, we were trying to build a line through, and it's a straight line. You guys see that? But in classification, not even neural networks, just classification, we use that same machinery, but we're trying to build a line that separates the data. Which line do we want? We want the best separating line out of an infinite number of lines, right? And so that is why we do this through an optimization technique. Does this make sense? Now, this is still not a neural network. I just changed from a linear regression problem to a classification problem. But this is a linear classifier. You guys understand that? Linear classifier. Now, the problem is this linear classifier can work really well for a lot of problems. And you've used it already when you did the logistic regression in Weka. Do you guys remember that you had to do logistic regression? That was a linear classifier, which basically means that you were doing this. See that? However, what I'm going to talk about today is the fact that not all problems can be solved, and I'll demonstrate that not all problems can be solved through linear classifiers. And that's the thing. For many years in history, people wanted to solve things with linear classifiers. Like the mathematicians, they were obsessed with this. And so they wouldn't pay any attention to neural networks, right? Because they were obsessed with this mathematically beautiful framework that they could use. But experimentally and with computing power, neural networks solve these things. So, you know, it became like a thing that they just had to do. So as I said before, I had this and I have that. So I can build a classifier, which is just a line that does the classification, right? Perfect accuracy. Now I could also do one like this, but this classifier is not as great, right? So what do I need to do? I need to shift it towards that direction. Do you guys see that? And that's all done, again, through that equation, right? The line equation, we just have to learn a new set of W's and a new set of biases. Got it? All right. So let's assume that we have, in fact, discovered a pretty good classifier. That's a linear classifier. So then you might say, well, that works for everything. But what about the problem where we have, oops, sorry. Yeah. What's the best classifying line for that straight line? Tell me where to draw a classification line that has no error here. Where do I draw it? If I draw it like this, are some items misclassified? Assuming these are circles, these are misclassified. Assuming these are the X's, then these are misclassified. Do you see that? Okay, so that doesn't work. Well, you might say no, but there's got to be another line. So how about I draw that line? These are correctly classified as circles. What do you have here? All X's are correctly classified, correct? But only half of the circles are correctly classified. You see that? So this is the classic XOR problem that I was talking about. All right. So there is no, as it turns out for this one, there is no perfect linear classifier. Logistic regression here will not work. That the one that you used in Weka. And so what do you need? You need a classifier that can approximate another function. As you guys know, the y equal mx plus b is a function, correct? But it's the function for a line, a straight line. All right, so then that function will not work for this problem. If this is $1 million, right, something in the stock market that gets you money, if you use that linear classifier, you're losing a few million there that you're leaving out, right? Do you see that? Because you have errors. So what would be now imagine what's the perfect line, not straight line, could be curve-ish, so that would separate this data perfectly. How do you draw that line? Like that, right? There's a little bit there. And then, yeah. And then, yeah. And then, yeah. Well, actually, I didn't do that. That was not optimized, correct? Or maybe something like that. Or how about, and it's hard, right? Even I'm a human, right? Like to think that I have a working brain, and I'm having a hard time here drawing something, right? And yet the machine learning algorithm will be able to figure this out, believe it or not. But what is the element, the relaxation or the add-on that we have to add to this? It's no longer a straight line. Did you see that? It now has to be a curve. But we can't just draw a curve like that. As it turns out, intuitively, that's why I started drawing like several little lines, because at the end of the day, what it's doing is it's like doing, you know what I mean? It's kind of learning this. And then it's gonna use these, you know, to eventually draw the entire line. Make sense? So that's basically what we're doing. But for that to happen, you know, you can think of this as a sum of all these little curves, right? This function that we see here needs to have certain things happening. And in particular, to become a neural network, we need to take this data that is called linear data and convert it to nonlinear. So the best intuition is, instead of drawing that straight line, we need to give the framework, the mechanism, the ability to draw these curves. Do you see that? And how do we do that? Quite simply, by adding a step. So believe it or not, this is what creates a neural network, right? We just go in here. I'm going to call this one now Z, just to kind of indicate that it's like a step in between. And then this C will go through an F function, and then it becomes Y. This function will map the data from something linear to something nonlinear, so that it can draw actually these curvy shapes in the data to achieve better performance. So remember, the goal is still to have zero misclassifications, but we need a function. If we just use this function like this, it can only draw straight lines. If we run the output of this function as an input to this function, then the data now takes on this nonlinearity. And by adding also the deep layers, that is what allows us to create something that looks like that. Does that make sense, guys? So that's what makes, in essence, a neural network, okay? So that's what makes, in essence, a neural network. All right, so then a neuron, basically, if we want to formalize it, can be thought of, so the neuron can be thought of, you know, I'm just using Z as the sum, basically, of all the W's and the Xi, right? So from I equals 0 to N. That's the formalization, which is basically just that equation. W vector, remember, it's all vectors now because it represents the features. Imagine if you ever get confused with this part, just think about MNIST. 28 by 28 becomes 784. So you have 784 features or X's, and you have 784 W's. Do you see that? And then at the end was one bias. Not one for every 784, just one at the end when you do that multiplication, okay? And that basically are the parameters that allow you to define your function. To make it a neural network, we run it through the function, okay? Which allows it to create these curvy approaches, okay? So that's one thing, right? That this basically you can think of as it adds the nonlinearity, and then remember we also do the layers, right? The layering system, right? So that's creating where we have something like Y1, we have W, X plus B. I'm just going to write it like this because it makes it a little bit easier. F, do you see that? And then the next layer then, W2, is going to be F. It can be the same function or a different function. Okay, we'll see that in a sec. Another set of W's is not the same set of W's. And what is this value now? Instead of X? Y1, exactly, because this is the input layer, this is the first layer, and this is the next layer, right? So they need to be connected in that way. So Y1 plus B, and so on. And that's so these two mechanisms, the little function over here, change color, And this idea of one function feeds into another one is what creates our deep neural networks, believe it or not. Okay, it creates the architecture that we are using. So now let's talk a little bit about this function f, just to give you a little bit of insight, right, of these functions. And then from there, we're going to move on to the XOR problem, right? So that should be fun. We're going to program that, and that's the classic XOR, and it'll demonstrate, right, that you achieve better results by using the deep neural network in TensorFlow itself. Okay, so I'm going to go here. So again, so now I'm going to just focus on these functions. These functions are sometimes called the activation function. You know, designing a neural network is basically like a job of, it's like you're an architect, right? And there is no like set in stone approach, right? Instead, you should experiment with it. But sometimes it's good to have certain intuitions about what your data should look like. Remember, also another thing I should stress, especially with deep learning, your data should be normalized. And remember what that is, right? So you know, normalizing the data, the inputs, the outputs, it's always a good practice. All right, so now we're gonna focus on the F function, these activation functions, just so that we have a sense of how they work. And you've looked at this before, I'm pretty sure, in your trig classes or something like that. So the function f. Function f. We're going to go through, basically these functions are the ones that you will be using, for this semester and, later. So these are the, you have a linear function, and then now you're going to run it through these. So basically the function can be, there are several. One is called a sigmoid. One is called a tanh. These are just the more popular ones that we're going to talk about today. One is called a relu. And we're also going to talk about the softmax. Since I can go back to the previous one, they're basically functions that take in as an input of some kind and just transform it to something else. Okay, and these functions, have a specific output that they produce, but it's intuitive. And I'll give you one example that I think will be pretty intuitive for you, which is actually very necessary sometimes. A lot of the times you're working on a problem and you're like, what is it? And these are usually the thing where you have to normalization, these activations, that's where it is really. So there are three major types of activation functions that are used in practice, and it's these: the sigmoid, tanh, relu, and softmax. Relu is actually the most common one. There's now Gelu, which is the Gaussian activation linear unit, but I'm not going to talk about that one today. So we're going to just talk about these. And for the most part, you can just get by with relu. Okay, and then the softmax at the last layer. And but sometimes you could use tanh. They have different properties. Okay, so let's talk about the sigmoid neuron first. Okay, so the sigmoid. This is the classic S shape that you probably saw somewhere, the sigmoid function. All right, so the sigmoid function has a, now, I'll write, I meant that to be, I'll write the equation sometimes, but in general, in TensorFlow, and we only need the function, right? So there's going to be a sigmoid function. It's going to be something like nn.sigmoid. We'll see that in the code. It's actually recommended that you don't write the equations and that you use the system functions, because sometimes you have divisions by very tiny numbers that give you underflow problems, and then you get like not a number and things like that, right? So whereas if you use the system built-in functions, then the system handles those things usually. All right, so what is the sigmoid? The sigmoid is the function, and you guys can help me out, it looks like this, right? So 1 plus e minus z. So what does that imply, right? This implies that we have, imagine, we're talking about a higher dimensional space, right? That means, let's say we have 100 features. So we have w x plus b, right? Everyone with me? And now this c value goes into this f to obtain y. So that f now just looks like that. That is the sigmoid function. Why is that important? It's important for the following reason. It has an actual graphical interpretation. I'm going to draw it like this. Okay, this goes from 0 to 1. Okay, 0 to 1 on that axis. Let's call it the y-axis. And this on the x-axis goes from minus infinity to plus infinity. But this function has a specific behavior that kind of, this may not be to scale. There. So it kind of looks like this, like an S shape. Like that. Do you see that? And then this. So as it starts to get negative, it never quite reaches 0. Never. It approximates it. It goes to the limit of 0. It never quite gets to 0. And when it starts to grow on the x-axis, it basically just never quite gets to 1. It just keeps going towards 1. Do you guys see that? So the important thing about this is we get, for instance, a value that could be from minus infinity to plus infinity. It will be converted to a value between 0 and 1. Do you guys see that? So intuitively, this means that when this value, which is sometimes called the logit, is very small, the output of a neuron will be close to 0. And then when it's close to 1 or to infinity, it's going to be close to 1. So, and then anything in between will follow this shape here. Okay. So this is very important in machine learning, right? And just think about it. You're now creating a machine, literally a machine, that you give it any input, pictures of cats and dogs, airplanes, iris, whatever you give it, it's always predicting an output, right? Or several outputs, right? And these outputs have what characteristic? All these outputs now, if it goes through the sigmoid, what do they look like on the output? So think about it. So I have I have something like this, right? A neural network. And then I have 3 neurons, right? Before, this was 500, 7,000, 3 million. But when I encapsulate, and I'm going to encapsulate, I'm just going to say like that. When I encapsulate these neurons, through this function, what happens to these outputs now? Between 0 and 1. Perfect. All of these now, that's meant to be a range. 0 and 1. So that means that these neurons are now what? 0.5, 0.7, 0.8. Do you see that? They're always between 0 and 1. Why is this important? Well, there's a nice intuition for this. If the last layer, the output layer, is 3 neurons, like iris was, right? Then remember, we can interpret this as saying, okay, if this is setosa, virginica, and versicolor, right? And we have a network that produces 3 outputs, but it's supposed to tell you one of these is the class, then how do we do that? Well, we could train the model to say, hey, this should be a virginica, right? So that's going to be 0, 0, 1. Now this is binary now. Okay, 0, 0, 1. So basically, the neural network has now a framework that learns these probabilities. It can just randomly generate probabilities, correct? Like if you don't give it data, it produces randomly values between 0 and 1 for every neuron. You see that? But as we start to train it, what happens? We give it an input and we give it the output that it should resemble. So over time, as it's iterating, what's it doing? It's changing the weights, correct? Weights change, 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 change. Eventually, what do you want? What do you want for these two probabilities to happen? Remember, this is the real. I'll maybe scratch this out because these are the neurons and you get that. I'll erase it. So it's not confusing. So this is how machine learning works. Hold on. Okay, so this is the predicted, this is the real, okay? So you basically build an architecture, a neural network, you give it inputs, they go through the whole network, they're supposed to predict these three neurons, correct? What do they predict there? Values. Because you're using the sigmoid, they predict values between 0 and 1. With no data, random stuff, but they're at least between 0 and 1 for all three. Yes? Now, what happens in learning? You give it inputs, it's got weights. Yes, it's got weights. It produces these values, but it's going to compare these three values to this one over here. And what is it going to learn? It's going to learn that 0.5 should have been lower, 0.7 should have been lower, and 0.8 should be higher. Because 0.8 needs to be 0.9999999, which is basically 1. And these two should be 0.00010001, as close to 0 as possible. It doesn't quite get to 0 or 1, but it gets pretty close. Do you guys see that? So this is how it learns. So it's almost like we create this pipeline where we give it inputs, and as we change the weights, it starts to produce things. If they start to mimic this one, then it's learning. And the loss function will go down, right? Because we've minimized the error. What happens if we get a lot of these situations? The loss is really high. Do you see that? Because it doesn't match exactly. Okay? All right, good. Now, another thing that's going to happen eventually is that here, for instance, let's say that it's kind of learning. Initially, it was like off, but now it's kind of learning. So what you do actually is there's 3 neurons. Out of the 3, you select the one with the highest value. So in this case, we would select 0.8. Do you see that? But the other one is 0.7. Pretty close, actually. You can interpret these as a type of a probability. So in a sense, you're saying, I think that it is this is class 1, class 2, class 3. Well, I think it's class 3 with a probability of 0.8 and class 2 with a probability of 0.7 and class 1 with a probability of 0.5. Do you see that, guys? Now, that doesn't quite make sense, though, because probabilities are out of 0 and 1, so they should add up to 1, correct? Do you guys see that? So that's a slight problem with Sigmoid, that Sigmoid just gives you this. You can interpret these as probabilities, but not quite, because they don't add up to 1. You see that? So we need something better, and that's where we get the softmax. The softmax is like a sigmoid with the added capability that it's going to, the values now will add up to 1. So it's better as an interpretation of probabilities. Do you guys understand? So this is how it works, right? So you build this machinery that will take data through and produce numbers between 0 and 1. That's it. You're the architect. You decide how many outputs you want, you know, what the inputs are. Let's say it's images, and the output could be 3 neurons, 10 neurons, 15 neurons. That depends on the number of classes that you have. You set it that you don't, now if you don't use the sigmoid, these values could be anything, right? It can be 500, 1000. It's a regression problem. When you don't scale them like this, it's a regression problem. When you scale them like this, now you can use this for classification. Any questions? All right. Now, as I said, the only problem is that for this to be more interpretable as a probability, we want these to be probabilities but also that all of them should add up to 1. But we conveniently have this nice little function called a softmax, right? And we'll code that up in a second, just so that you guys can see how it works, all right? But anyway, these are the activation functions. As you can see, they transform the behavior. This is no longer a straight line, right? Do you guys see that? The data is no longer a straight line. It's more of a curvy S, and they add the nonlinearities. Okay. All right, so that's the sigmoid function. Let's look at the next one. What was the next one? If you're paying attention, tan H. All right, so that's the tan H. So what's the difference between the sigmoid and the tan H? Anyone know? Nope. All right, so tan H has its usefulness, actually. So in sigmoid, the interpretation is a probability. Do you guys have negative probabilities? Have you ever had a situation in life where you're like, there's a negative, so you have a probability usually between 0 and 1, right? However, some outputs, you may want them to be negative. You see that? But also between a small range, right? That's where the tan H comes in. So the tan H actually, you could argue that is an activation function to use in the hidden layers, because in the hidden layers because you can also use activation functions pretty much anywhere, right? And so you might want the weights or the values that go in here to be negative or positive, right? And so you can also scale them in that way. So the tan H function or activation function is I'm not going to write the equation for this one, but I will write the diagram. This is the tan H. And now you have, let's say, minus 5, 5, and minus 10, and all the way to minus infinity, plus infinity. We're still using that Z, the Logit as it's sometimes called, to indicate the value that goes into the activation function. So basically this becomes the Z-axis, right? Makes sense? But we're going to map this to another scale, if you will, call it Y. And now here, this scale goes from 1 to minus 1. You see that? That's the only difference. The shape is still pretty similar to the sigmoid. Is a type of an S shape. Like that. Does that make sense? So what's the value of this one? This one takes an input from your original function, right? So Y, oh, no, Z, right? Z equaled, times W plus B. That's a vector. When I put that little arrow on the top, it means, 784 features. Goes into this function, and now this value will be in the range of what? Yes, -1 and 1. So from -1 to +1. And there's a use for the value for this is that now you'll have these numbers. They're all in this scale, but they can be negative or positive. You see that? As you're building your architectures, and you'll have to think of your problems to kind of figure out which approach you're going to take. For many years, researchers and people argued about this. What's the right, and they wanted to do proofs and everything. In the end, they just experimentally concluded that they have their uses, mainly, I should say. So I'll say this as well. So you have this, right? And then in between, so this is inputs, this is outputs, and then however many hidden layers you want, right? Right? So in the inputs, you do take the data and you normalize it. That's a type of this, right? So you're going to run your data and just normalize it. There's two approaches to this, standardizing and normalizing, actually. So usually you say normalizing, but there's two techniques. We'll talk about those later. This is you should always do that. That's the normalization part. And then you have all of these have activation functions. In general, though, here you can use the sigmoid and the softmax. So in the last layer, you generally want to use that one. Do you see that? Because if I'm basically talking about a classification problem, because we want to do that thing of estimating the probabilities that it's this class over the other one. In the hidden layers, so H1, let's say H2, H3, you actually use the following activation function called, I'll just do like this, the ReLU. How do people know this? Experimentally. They just concluded that that was a pretty good one. And so generally speaking, you should try it. You know, that's what you should probably go with. Does that make sense? But that's another activation. Really, it does the exact same thing, right? For the outputs of this layer, you're going to transform those and through the ReLU function. So let's take a look at the ReLU then. ReLU stands for the rectified linear unit, or the famous hockey stick, right? So so sometimes people say it's the hockey stick function, and the reason being, what it does is something like this. So we got the Y there, and I'll draw this in another color. There you go, a hockey stick. See that? So what is the interpretation? It's a different, it's still a nonlinearity, even though it looks straight, right? So you might say, hey, that's no, but it is nonlinearity. Because remember that the curves that you're creating, you're actually creating kind of as a sum of all of these, right? This is called a restricted linear unit, or so-called ReLU, and it uses the following function. It's actually pretty easy. You know, a lot of the time you hear the word ReLU and you're like, oh my God, that's got to be such a hard concept to grasp, right? And it's surprising how simple it is. Max of, oops, sorry. Zero or Z. So basically, if your Z is negative, 0. And if your Z is positive, Z. You see that? So it's like, it's linear. So that implies that, you know, 1 to 1. You see that? 2 to 2. So it's linear. So if it's up 1, 1. But if it's negative on the negative side over here, then it's going to be a 0. Okay? So yeah, that's it. That's the ReLU. Any questions on that one? All right, and so this is important, actually, really important. It's important that you guys get these concepts. All right, so yeah, so that's kind of the theory for today. Not too much, just enough, but really important. Okay, those are the basic mechanisms. The next, I'll do a little bit more theory on Thursday, and then we're just gonna get started with. Oh yeah, I'm sorry. Yes, I draw the zeros like that to separate them from O's. It's a coding thing. It's a 0. Yes. All right. Yeah. So now I already gave so we're gonna move on to softmax. Okay. So I already kind of talked about this one. Softmax, right? And this is important in that last layer for a classification problem. You want we already know that we can make the probabilities from 0 to 1, but we want the probabilities to actually add up to 1. That's the only. So oftentimes we want that output vector to be a probability distribution, is what it's called, over a set of mutually exclusive labels, right? So when we have, you know, like 3 classes, versicolor, virginica, setosa, right? So how do we do this? So I think the best way to understand this for this example is just to do the code itself. There's a formula, so I'll give you the formula. And the formula looks like this. And this is just the sum over all the sums of all the other ones. J. So one is I, one is J. All right, this is for each individual value, right? But let's, if, you know, it's probably better just to do this in code, and we're going to get a feel for how we can translate this. All right, so let's think of the following example. And then from here, we're going to move on to the XOR problem, okay? And that's going to be in TensorFlow. So let's, this is the softmax. Let me change the color. So softmax. Okay. Remember, this is for the output layer. So we had a neural network. We have a neural network that looks like this. Some input, some hidden layers. Right, so I have hidden 1, hidden 2, hidden 3. And then we have the output layer, which basically has 3 neurons, right? So this neural network produced 0, 1.0. Yeah, actually, this one is not even assuming that there's going through the sigmoid. It's just no sigmoid. Okay, this is just like a regression is producing values. Right? Because we don't have to do a sigmoid and then softmax. We can just do the softmax and it covers the sigmoid part. Okay? So if we look at this one, remember, this is your y vector, right? Now this adds up to what? 3.1, right? It doesn't have the interpretation that we want, assuming that we want to select one of these as the class. Okay? And so what do we need to do? We're going to take this vector and let's call it, you know, y, z here. And we're going to run it through the softmax. Make sense? And the translation for it should be that we are going to get, and write this down so that you can corroborate, 0.7, 0.2, 0.1. As you can see, I don't know. Huh? What did it say there? Is it still recording? Still, right? Yeah. Yeah, sorry about that. Okay, so as I was saying, if you look at the values, 2, 1, and 0.1 are now 0.7, 0.2, and 0.1, right? They add up to 1, which is what we want. So if these are the classes C1, C2, C3, which one do you select as your class for this model? C1, right? How do you do that? You do argmax of that vector. Argmax returns the index of the highest value. So it would return index 0. That's your class C1. All right, that's it. It's literally that easy. All right, so now that we have this, I think that's all the theory for today. So we can go to the Jupyter Notebook. We're going to create a very simple Jupyter Notebook and just do softmax, okay? So let's do this. All right, so I need to... Question? Yeah, so I'm going to stop this. And I have this one, so I need to share that screen, or this one. All right, so, okay. So we are now in the prompt, the Jupyter prompt. So I'm going to do dir CD 2023. There. Yeah, so just in here. The Conda environment. And we've already created a TensorFlow environment, I believe, right? Last time. So we can just do that. So Conda activate. 538 TensorFlow. Oh yeah, 374. TensorFlow, right? Okay, and then we can start a Jupyter notebook. All right, yeah, so I'm gonna create a new notebook here. New Python 3. And this is just to demonstrate softmax. I do think softmax. All right, so let's add a few layers. All right, so what we want to do, this should have TensorFlow already. So let me just do import TensorFlow as TF. Okay. All right, great. So it's working. We're just going to do this in NumPy actually. So let's do import NumPy as NP. And now our original vector was 2, 1, and 0.1. So that was the logits, right? The Z, right? So we can call it Z or logits. Right, so we're going to call it logits. And this is going to be the original vector. So 2.0, comma, 1.0, comma, 0.1. So imagine this is what's the vector that you get in the output layer, the 3 values, right? But you want these to add up to 1. So then we're going to apply that equation. We're going to do the exponentials. All right. So that's going to be a list. And each one of the values in logits, so we're going to do a list comprehension. So for I in logits is np.exp exponential. Remember, it was an exponential. We'll go back to the equation if you forgot. And we run that particular I. So we're raising it to the exponential, right? All right, so I do that. Did I not run this one? I think I did. Yeah, there we go. Okay. So I've got the exponentials, and I don't get this. I don't know what is going on with this computer. What do you guys think? Should I restart it or? All right, so I'll do this.